Einstein's theory transformed traditional views of space, time, matter, geometry, and physical reality. In the classical picture, space and time are treated as containers and matter as their content, with energy and momentum regarded as fundamental features of matter. General relativity disrupted this framework by making space-time geometry inseparable from gravitational phenomena and by raising new philosophical questions about what should count as real. Early interpretations of the theory differed widely, with some philosophers emphasizing the relativization of inertia and simultaneity, others developing Neo-Kantian readings, and logical empiricists focusing on the methodological significance of the theory. Reichenbach interpreted general relativity through the relativity of geometry and tried to ground it in observable facts involving rods, clocks, and light rays. Hermann Weyl pursued a reconstruction of Einstein's theory through infinitesimal geometry, linking geometry with the electromagnetic field. In structural realism, especially ontic structural realism, the fundamental level of reality is not made of individual objects with intrinsic identities, but of structures and relations. This view is especially relevant to general relativity because of the theory's diffeomorphism, invariance, and background independence. From this perspective, the distinction between objects and their properties or relations is not ontological but conceptual. We have to mention the role of Cassirer, Carnap, Schlick, and Reichenbach in debates over whether general relativity supports critical idealism, empiricism, or a new philosophical understanding of scientific concepts. Einstein was rejecting simple scientific realism while still believing that theoretical science gives access to nature beyond immediate empirical data. His view allowed for underdetermination in principle, but he maintained that in practice, experience guides scientists toward one superior theoretical system. In the Einstein's correspondence with Schlick, it is introduced the distinction between what is directly given in experience and what is constructed within a space-time framework. Einstein's point coincidence argument gives ontological priority to space-time coincidences because they remain invariant and can be unambiguously determined. After the emergence of general relativity, there was a debate if physics might be reducible to geometry. While the stress-energy tensor of matter is a true tensor, the gravitational stress-energy quantity is only a pseudo-tensor, which means gravitational energy cannot be localized in the same way as ordinary energy. As a result, general relativity challenges the classical notions of total energy, momentum, and gravitational force. Gravity is no longer understood primarily as a force, but as a geometrical feature of space-time, although in special limiting cases, the language of force can be partially recovered. Two accounts of the metric are important. One in which metric structure is constituted by relations among material entities such as clocks and light rays, and another in which the metric is an independent physical field postulated to explain observed phenomena. This dispute leads to the deeper ontological issue of whether an empty space-time with a well-defined metric is intelligible, or whether space-time points require material entities for individuation. Newer dynamical approaches, associated with thinkers such as Harvey Brown and Oliver Pooley, argue that space-time structure may be derived from the fundamental laws and symmetries of matter, rather than being ontologically prior to them. In conclusion, general relativity appears not merely as a physical theory of gravitation, but as a theory of space and time in which space-time emerges from the total structure of events and their metric relations.